Bien, vamos a escuchar entonces las exposiciones de Max Bothwell, de Pedro Di Carli y de Daniela Guajardo. Los invito a Max a que nos acompañe aquí al estrado para comenzar la exposición del día de hoy. El doctor Max Bothwell ha trabajado en investigación medioambiental en Canadá desde el año 1979 y su posición actual es profesor adjunto del Departamento de Química, Pesquerías y Acuicultura en la Universidad de Vancouver. Es especialista en ecología y fisiología filantopláctica, con énfasis en dinámica de nutrientes. El Didymo llamó su atención en el año 1993 estudiando las causas de los blooms en ríos canadienses y durante los años 2006 y 2007 fue consultor técnico en bioseguridad para el gobierno neozelandés, cuando el alga invadió dicho país. A partir de sus investigaciones ha deducido que la causa subyacente de los blooms de Didymo está relacionada con la baja concentración de fosfatos en el medio, lo cual respondería a cambios ambientales de gran escala conducidos por el nombre. Tiene a su haber más de 15 publicaciones científicas solamente en la temática del Didymo. Max Bothwell nos va a presentar a continuación su exposición.
I find myself in a position of making a presentation that's going to be a little different than what a lot of people actually have heard about Didymo. But it's been a mystery that I've been involved with for probably half of my career, and it's taken some real different turns. And I'll lead you by the hand here as we go through this chronologically.
A little bit slower, please, because I have to translate.
Yeah. Oh, okay.
Entonces, él está dando la bienvenida a todos acá. Vamos a ver una presentación que es un poco diferente respecto a la experiencia que se ha visto en Norteamérica respecto al Didymo.
The beginning of Didymo blooms, the recorded Didymo blooms in the world actually started in Canada on Vancouver Island in the early 1990s.
El comienzo del florecimiento del Didymo comenzó en 93 en Canadá.
I was called in to look at this because at the time I was one of the authorities on the role of phosphorus in creating diatom blooms in rivers like this.
Fui llamado a investigar esta situación ya que yo estaba involucrado en el ambiente del fósforo y era uno de los compuestos que estaba relacionado con el Didymo.
This situation, however, was different than anything we had ever experienced before.
Esta situación era muy diferente a la que hemos visto en cualquier otra situación.
Because there was no source of nutrient coming into these rivers.
Porque no había ninguna fuente de nutrientes viniendo del Didymo.
Didymo bloom started on Vancouver Island at the confluence of the Heber and Gold rivers.
El florecimiento del Didymo comenzó en Vancouver, en la isla de Vancouver, en 1988.
You will see this image near the end of the talk in a very different context.
Van a ver esta imagen al final del seminario, al final de mi presentación, y la van a ver muy distinta a la que la ven ahora.
Within 10 years, Didymo blooms had been recorded in the majority of rivers on Vancouver Island. Most of this had occurred in the first 8 years or so, but within 10 years, and that's a time frame you can easily remember. 10 years from the time that blooms start, they are wherever they're going to be.
Durante el periodo de 10 años se pudo ver el florecimiento bastante amplio en esta zona.
I was fortunate in Vancouver Island because of this monograph by P.T. Cleve on the naviculoid diatoms, published in Stockholm in 1894, 1896. And in this monograph, Cleve describes what this diatom looks like, and he indicates where he's found it. And the last entry in this is Vancouver Island. So at the very beginning, there was no question that this was a native organism.
Él recibió un monógrafo en el que se puede ver que el Didymo estaba presente en la isla de Vancouver desde hace muchos años atrás.
So if Didymo blooms were new on Vancouver Island, what caused them? The usual suspects for diatom blooms are changes in flood disturbance or changes in nutrient levels.
Estamos viendo por qué por qué se inició el Didymo en estas condiciones. Lo que podemos ver es que había cambio de la fluidez y de los cambios de niveles de nutrientes.
When I started out studying this, I proved that there was no change in flood disturbance associated with the onset of these blooms, and there was no change in nutrient levels in these rivers either, none that could be measured.
Ninguno pudo probar de que existía una diferencia en los cambios de la fluidez y tampoco los niveles de nutrientes. Entonces eso se descartó.
I had also been working with graduate students on the effect of solar ultraviolet light on the growth rate of diatoms that create stalks, like Didymo is one. And we ran an experiment in the late 1990s to find out if changes in solar UV light associated with ozone depletion might actually be tied to this. No.
Con un grupo de estudiantes hicimos un experimento con los rayos solares después de los años 90 y tampoco se hubo un cambio en los florecimientos con elevados rayos solares.
So in 1998, there was no known explanation for these blooms.
En 1998 no había una razón clara de por qué existía el florecimiento del Didymo.
And then in 2004, things changed. That was the beginning of the incursion of Didymo into New Zealand, the South Island of New Zealand. And I was called in to assist Biosecurity New Zealand in an advisory capacity looking at this.
En 2004 fui llamado a presenciar el Mararoa río, en el cual se puede ver en las imágenes, y ahí empezó a cambiar el por qué existía el florecimiento del Didymo.
When I came back from New Zealand, back to Canada, I wondered, was a variant of Didymo introduced to Vancouver Island in the 1980s and I didn't know about it?
I'm sorry, can you...
They're in Spanish. Okay. I didn't know about it. Was that the explanation? And were these the culprits? This is what everyone was talking about, that these people were moving this around. And were these also responsible for the Vancouver Island experience?
Los culpables principales, como se pueden ver en la presentación, era la pesca y el hecho de que nosotros como personas estábamos trasladando esta bacteria.
So I went to the data records for fishermen in British Columbia, and I put together this historical record of numbers of fishermen fishing in rivers on Vancouver Island who were not Canadian. They were from some other part of the world. And in fact, there had been a large increase in the number of fishermen during the 1980s visiting Vancouver Island from other parts of the world.
Como podemos ver en la tabla, él reunió datos en el que pone número de la cantidad de pesca que existía en los ríos durante esos años.
And this coincided with the commercial introduction and widespread popularity of felt-soled waders that happened in the 1980s. And I put that story together with the global story. This is a graph of Sarah Spalding and Leah Elwells in their white paper in 2007. The red dots are blooms of Didymo recorded around the world. The red circles are mine that indicate where blooms have occurred after Vancouver Island.
Los puntos rojos son donde se puede ver que existe el florecimiento del Didymo, y los círculos que él marcó son donde él descubrió los florecimientos después de haber descubierto en Vancouver.
And that would be most of them. So it looked as if Vancouver Island was somehow the epicenter of Didymo blooms occurring around the world. And I put that story together and I wrote this paper that many of you have seen. It was well received throughout the fishing community and around the world, actually, in Los Zapatos de los Pescadores. And I was happy with this paper for two reasons. First, there finally was an explanation for why I had not been able to understand this 10 years before.
Él escribió este papel, el que está muy orgulloso y que muchos de ustedes ya han leído, y por fin pudo ver por qué no había una razón del florecimiento del Didymo.
The second reason I was happy with this was I was very happy to provide support for my friends in New Zealand who were taking a lot of flack for their banning of felt-soled waders. And this paper probably appeared on the New Zealand Fish and Game website before it appeared anywhere else.
Este papel que él escribió apareció también para Nueva Zelanda, en que ellos estaban muy agradecidos por la información dada por el señor Max.
The problem with this paper, however, and all scientists know this, is that correlation is not causation. And this paper is based totally on correlation. Now I'll talk about the research that we've done since this paper was published that leads to a different interpretation of what we've been seeing. This is work that was done in New Zealand with Kathy Kilroy. In 2008 is when we started this project on the studying Didymo on a braid of the Waitaki River. And what we were interested in doing at this location was trying to understand why Didymo would not grow in spring-fed creeks that were tributary to Didymo-affected rivers, even though there were some locations in these spring-fed creeks which would appear to be physically suitable places for Didymo to grow. Didymo was introduced all the time, but it never established itself there. Why?
Este proyecto lo hizo junto a Miss Catherine el 2008, en el que estudiaron las condiciones del río Waitaki con las condiciones que no eran adecuadas para el florecimiento del Didymo.
So this apparatus is one I designed, was built in New Zealand to run a very specific experiment. There are two water sources here. One is the river water, which has lots of Didymo but very low nutrient. And the other is the spring water, which has no Didymo, but it's spring-fed, so it has high nitrate and higher phosphorus.
En este proyecto se realizó con 2 zonas de agua, una cubierta con dídimo y bajos nutrientes, y la otra 0 dídimo y altos nutrientes.
So the way the experiment was designed, it's important because this was a critical experiment that actually changed everything about how we look at this. All of the experimental channels were colonized with Didymo by using river water, because that's where all the Didymo was. And then once colonization was complete, we switched the water source over to spring water in some of them and left others as controls.
Entonces el experimento fue lo siguiente: se trajo agua que estaba contaminada con el dídimo a la zona que estaba limpia.
Okay. And I was all set to sit back and watch spring water kill Didymo cells because that's what everyone knew happened.
Y lo que se pudo observar es que en la zona de agua limpia destruyó por completo todas las células del dídimo.
But that's not what happened. The troughs, the experimental channels that were switched to spring water, Didymo cells exploded into growth. Within about 11 days, more than 40% of the cells were in some stage of division. I had never seen anything like it in nature. And the dark ones that you see here are the ones that were switched to spring water. Didymo cells loved spring water.
Como podemos ver en la imagen, las columnas más oscuras son las que están completamente tapadas con dídimo, ya que dídimo le encanta el agua de corriente.
But about 2 weeks after this photograph was taken, the Didymo in the spring-fed troughs had gone. So what appeared to happen was that what was really good for Didymo cells, causing them to grow very rapidly, prevented colonies from forming. And this is what I saw under the microscope. Didymo is a really large diatom, as you know. Very easy to see it in various stages of cell division.
Como podemos ver, el dídimo es una diatomea y es muy fácil de observar por el microscopio, ya que tiene una forma muy particular.
And we employed a technique called the frequency of dividing cells, which is the percentage of the population which is actually dividing, and use that as a metric for how fast Didymo is growing.
Utilizamos una técnica para ver qué tan rápido podía crecer el dídimo en esas condiciones.
And with this metric, Kathy and I embarked on a whole series of experiments to determine the effect of phosphorus, nitrate, light, and on the growth rate of Didymo cells.
Con Katy trabajamos con diferentes proyectos en el que se veía, se implicaba fósforo y nutrientes altos y bajos.
This is a braid in the Waitaki near our site where we ran these experiments. Kathy and I worked at this site for a couple of years, and it's easily weightable across this thing, and you can see a gradient in color along the bottom, and that's not an optical illusion, it's a reflection of what's on the bottom. And this is this composite image here is Kathy holding up stones along that transect so you can see what's on the bottom of the river. Now this picture is taken looking downstream, and the Odiak Spring Creek with the higher nutrient is coming in on the true right bank, on the right hand side.
Como pueden ver, un cambio de color en el florecimiento del dídimo, y ahí podemos ver lo que está debajo del agua en bajo corriente. What type of nutrients are you mentioning here in the picture?
The nutrients are total dissolved phosphorus, soluble phosphorus, and nitrate nitrogen. The numbers, okay, The concentrations of nutrients in the time that most of the time that I worked here were extremely low and not measurable. And I didn't measure them here either. What I did is I calculated what they must be based on an n-member mixing model and concentration, known concentrations, measurable concentrations in the Spring Creek, and measurements of conductivity along the bottom of the transect.
That was too long.
Yeah, I know. So the numbers that you see here are computed numbers of what the concentration of phosphorus must be based on measurements of conductivity that I made along the bottom here. And what you see is that the stone on the right-hand side of the image there, where there's no Didymo colonies at all, the total dissolved phosphorus is about 2.8 parts per billion. Soluble reactive phosphorus there is less than a tenth, less than 0.5. Total dissolved phosphorus. If you go about 2 or 3 meters off this bank, you see Didymo blooms start, and that's where phosphorus has dropped from 2.8 to 2.5 parts per billion. That difference in phosphorus is the trigger for Didymo blooms. And Didymo blooms by the middle of the channel are really healthy because phosphorus is declining more and nitrate is enriched. The best conditions for it. On the far side, we see pale and anemic Didymo that's the result of nitrogen starvation. So the trigger, based on the data that's in this from this transect, the trigger that starts the blooms is somewhere is under 1 part per billion. And that's going from that rock there to that rock. That's the difference. This is a figure from one of Kathy and my papers. This is a synoptic survey data for multiple rivers in South Island, New Zealand. On the left-hand side, we plot the frequency of dividing cells. This is how fast Didymo cells are growing.
Como podemos ver en la gráfica, trabajó con Katy para ver qué tan rápido el florecimiento del Didymo crecía en esos ríos en Nueva Zelanda.
And because the growth rate is limited by phosphorus, the higher the phosphorus level, the faster they grow.
Entonces, mientras más alto el nivel de fósforo en los ríos, más rápido crecía el florecimiento del Didymo.
Yeah. It's very simple. What's much more difficult to understand is the figure over here. This is the same data, but it's looked at in a different way. Here we plot how fast the cells are growing against a standing crop index. This is a metric that Kathy developed in New Zealand. It's really the only decent way of actually measuring Didymo. And what we see here is that, I like to refer to this as the ugly index, because that's what it is. This is the ugly index versus how fast the cells are growing. So,
en el gráfico podemos ver qué tan rápido las células del Didymo crecían versus Can you mention again?
This is this is the standing crop index. It's the ugly index. How ugly Didymo looks.
Ya. Entonces el otro lado es qué tan feo se ve el Didymo, como podemos ver en las fotos anteriores.
See. So when Didymo cells are growing very slowly, they're really ugly. The blooms are really ugly.
Cuando el Didymo crece lentamente, las células se ven muy feas.
But as more phosphorus becomes available and the cells begin to grow faster and faster.
Mientras que hay más fósforo y las células crecen más rápido,
The blooms become less ugly
el florecimiento no se ve tan feo.
until finally they are growing so fast they vanish.
Que al final, si van avanzando mucho más rápido, desaparecen,
Like a magic trick.
como un truco de magia.
Here's some more data from this, the Synoptic Survey of Rivers on South Island of New Zealand. And what we plot here, this is from the same data from the same paper. We plot algal biovolume. Again, and this is a histogram for each of the rivers. And on this side here, we put the plot the average dissolved reactive phosphorus concentration in that river.
Como podemos ver en la gráfica, a lo que se refiere él es los diferentes niveles de fósforo y cómo reaccionaba el Didymo ante ello.
Didymo is such a dominant player in many South Island rivers. It has a color all of its own. And what we plot here is the red line, basically. And the red line for dissolved phosphorus from this survey is about 2 parts per billion. And what we found in this survey here is that any river on the South Island of New Zealand which has a phosphorus concentration equal to or greater than about 2 parts per billion, Didymo blooms do not form.
Como podemos ver, si el río tiene un alto nivel de fósforo,
See, even though Didymo cells are present in some of these rivers. After publishing these papers, these scientific papers, and thinking about what it meant, the whole thing, what it meant, I had this epiphany. And this occurred to me, it wasn't overnight, it took several months for us to crystallize what we had done actually showed. And what it showed was that Didymo blooms don't occur in spite of P limitation.
durante un tiempo tuvo una epifanía en la cual, Max, can you explain it again?
Okay. The epiphany is that Didymo blooms do not occur in spite of P limitation.
Spotlight.
In spite of, despite P limitation. Is that a better word?
What?
Didymo blooms do not occur despite P limitation.
Ok. Entonces, la epifanía es que a pesar de, I don't know how to explain it correctly.
Yeah, okay.
Sorry.
That's what everyone was talking about. Everyone in the literature was talking about how, because Didymo blooms were forming these things in low phosphorus water, they must have some special way of getting phosphorus, because that's what the academic literature on diatoms and nutrients is all about. It's all about competition for the limiting nutrient, which is always phosphorus. But that's not what this is. Didymo blooms don't occur in spite of P limitation. They occur because of it. That's completely different.
I got lost.
Okay. The proximate cause of Didymo blooms, the proximate cause is phosphorus limitation. The blooms are a consequence of oligotrophication, not some new variant with bloom forming tendency. That's got nothing to do with it. The Enlightenment. Now that we know the proximate cause of what's the blooms, what's causing them, now we can talk about the science of this. What are the potential mechanisms for oligotrophication? What's going on? The ultimate cause is something that's causing phosphorus in rivers to go down. And I'll talk about, there are four actually, but I'll only talk about three hypotheses that can explain this. Nitrogen deposition from the atmosphere, climate warming, and earlier spring snowmelt, and nitrogen enrichment of landscapes. I'll talk about each of these in a very short way.
Después de la Epifanía tuvo la ilustración en la que podemos ver las tres causas de los florecimientos del Didymo. Podemos ver deposiciones de nitrógeno, el cambio climático y enriquecimiento de nitrógeno en diferentes lugares de la zona de Nueva Zelanda.
Yeah. I'll start with atmospheric nitrogen deposition. This has been well known for at least 2 decades, almost 3 decades. The top illustration is an illustration from biogeochemistry, Galloway's paper, showing the time course of increasing nitrogen deposition starting at the earliest part of the Industrial Revolution and continuing on in the future. Most of this nitrogen deposition is in highly populated areas of the world, right?
Como podemos ver en,
sorry. Yeah, go ahead. No, go ahead.
Como podemos ver en las imágenes, un aumento en el nitrógeno generalmente en los lugares donde hay más población y más zona industrial.
So not particularly relevant here. The bottom illustration in Science is from Jim Elser, a paper showing that what happens when you add nitrogen through atmospheric deposition into lakes is that it drives phytoplankton communities into phosphorus limitation. Okay. Jim Elser is one of several limnologists who's shown this. And what I'm saying here is that Didymo is telling us the same thing for rivers. Another hypothesis is global warming. And this is a complicated one because there are several mechanisms that are likely at play here. Unfortunately, there's not a lot of data that goes along with any of these actually right now, and we're in the process of pulling together these data sets now. One of the parts of global warming hypothesis is how earlier spring snowmelt affects phosphorus concentrations in rivers.
Como podemos ver acá, él se refiere al calentamiento global, que tenemos mucha información y cómo el fósforo puede dañar los ríos durante el aumento del calor en el mundo.
When snow first melts in the spring, large amounts of phosphorus enter rivers at the same. That is the process for loading of phosphorus annually. It happens with spring snowmelt. But after that, after the spring snowmelt is gone, phosphorus concentrations in rivers fall to lower levels than they've ever been before. And this is the time of year, spring, when the sun is coming up and it's an opportune time for diatoms to grow.
Lo que se refiere él es que cuando hay nieve de primavera, el fósforo aumenta en los ríos y se produce el florecimiento durante los meses de primavera.
The other mechanism by which global warming probably affects phosphorus levels in rivers is this one here, hypothesis 2. And it's just a word slide because there are no data. And the word slide is that earlier warming of soils results in greater microbial and activity on land that results in higher binding of phosphorus in landscapes, less phosphorus to run off into rivers. And you'll see this in the next, in spades in the next hypothesis. This is the most likely explanation for large parts of North America and maybe even here.
Como podemos ver, la siguiente hipótesis no tiene ningún gráfico, ya que no hay mucha información al respecto. A lo que se refiere es que en las zonas de terreno hay un alto porcentaje de fósforo y en los ríos hay un bajo porcentaje de fósforo.
The last hypothesis I'll talk about is nitrogen enrichment of landscapes. This is my favorite, and it's probably the most relevant to the situation that started me on this journey on Vancouver Island. Jim Elser wrote a companion article in Science in the same issue that Holtgreave et al. Did their paper, and the article is entitled "A World Awash with Nitrogen." This is an extremely important paper. It should be required reading for young scientists.
Se escribió un papel referente al enriquecimiento del nitrógeno en diferentes lugares de paisajes.
And in this paper, Jim uses these two photographs to illustrate how the world has changed. And in the one on the right-hand side, this one here is an early model internal combustion engine as to symbolize the burning of fossil fuels and the loading of nitrogen to the atmosphere. We all know about that one.
Como podemos ver en las imágenes, ella muestra cómo el mundo ha cambiado respecto a esos aparatos.
The photograph on the left-hand side here, though, I've given this talk around the world, and no one knows what that's a picture of, and it's actually the most important one. This is a photograph of the bench scale apparatus that Fritz Haber used in 1908 to demonstrate that it was possible to combine nitrogen gas from the atmosphere with hydrogen gas that he liberated by electrolysis of water at high temperature and pressure using an osmium catalyst to produce ammonia.
Mucha gente no sabe qué es esa foto, siendo que es una de las más importantes, la que demuestra cómo se combina el nitrógeno de la atmósfera con el nitrógeno de los ríos a alta presión y se puede dar un resultado.
Carl Bosch joined the effort about 10 years later, and his contribution to this was showing that you could use methane gas as a source of hydrogen, and you could use iron as a catalyst. That made it possible to become an industrial scale process. The Haber-Bosch process is the most important chemical reaction in all of human history because it changed the planet. The estimate is that the human population of Earth is more than double what would have ever been possible without Haber-Bosch. The amount of nitrogen spread across the landscapes around the world is 2 times higher than it's ever been historically. Most of that's occurred in the last 50 years. And there isn't an ecosystem that hasn't been affected by this. A really startling statistic is that half of the nitrogen in every single human being on Earth today was originally fixed in the Haber-Bosch process. You and I wouldn't even be here, in all likelihood. Now we all know about the role of nitrogen fertilizers in agriculture. But what a lot of people do not know is the role that nitrogen plays in silviculture and rangeland management activities across broad swaths of the world. And Most of the audiences, like yourselves, who are familiar with the Didymo story, I asked them, have any of you ever wondered why Didymo bloom started on Vancouver Island 10 years before anywhere else? What's so special about Vancouver Island? Well, it turns out this. Starting in 1977-78, the province of British Columbia began a massive silviculture fertilization project, fertilizing timberlands, mostly on Vancouver Island, with urea nitrogen. Why do they do this? Well, they do it to increase timber production. Timber is the lifeblood of the economy of the province. They fertilize 5,000 to 10,000 hectares every single year. They're doing it right now. The formula is the industry standard for forestry. 435 kilograms per hectare. That's 200 kilograms of urea nitrogen per hectare. They add 2 to 4 million kilograms of urea every single year. And most people have a hard time conceptually understanding the magnitude of what I'm talking about. So I provide this illustration. One rail car holds 90,000 kilograms of nitrogen, of urea nitrogen, 90 metric tons. Starting in 1977-78, the province of British Columbia has applied 25 to 50 train loads of urea to timberlands on Vancouver Island. This is the cumulative effect of that. Starting in 77-78 through, I have data here through 2012, 45 million kilograms of nitrogen, fixed nitrogen, have been added, largely to timberlands out in the middle of nowhere. All done by helicopter. Starting at the 10 to 12 million kilogram mark, Didymo blooms began on Vancouver Island. What's the connection between nitrogen fertilization and oligotrophication? Rivers on Vancouver Island are phosphorus limited. We've known that for many years. Nitrogen added to soils results in tighter binding of phosphorus in land. The mechanisms might vary, but the forest soil scientists I've shown this to unanimously agree that the most likely mechanism is the mycorrhizal stimulation of phosphorus uptake. Fungi in the soil are doing this. And the higher binding of phosphorus in biological metabolism in soils is resulting in lower amounts of phosphorus that can flow into rivers. That's what the blooms are about. Now, I told you that you'd see this picture again at the end of near the end of the talk. Here it is, in a different context. Here we see a Google satellite image of that drainage. The red squiggle mark, I'm hoping that you can make out here, right in here. This is the Heber River. The Heber River, the confluence is this town of Gold River. The Gold River runs north and south. The Heber River joins it here. The Heber River watershed was targeted for urea fertilization in November of 1986. During that month, they fertilized 6 blocks with urea. They added 40,000 kilograms of urea nitrogen. The location of those 6 blocks is shown in red here. Didymo blooms commenced in the lower Heber River. These are the first blooms ever recorded in North America, starting about a year later. So I've talked briefly about potential mechanisms for oligotrophication, atmospheric nitrogen deposition, climatic warming, advanced spring snowmelt, nitrogen enrichment in soils. The important point, not all of these are operating, obviously, but the important point is that none of them are mutually exclusive, and they're all pushing phosphorus in the same direction, and that direction is down. In fact, some of the best known examples of Didymo blooms in North America are the result of improved treatment of sewage and taking pipes out of rivers that causes Didymo blooms. Now here's a graph that's a favorite of mine. It was in Sarah Spalding and Leah Elwell's paper. It shows the preference that Didymo has for low phosphorus water. We've all known that, right? It's something that we've all known from the very beginning. And I've shown this graph because it was the best data set I was aware of to audiences for years, actually. But why is it that all of us trained limnologists looking at this, PhDs looking at this, no one saw that the most likely explanation, the most parsimonious explanation for this would be this? I didn't see it either. And then I tell my audiences, I said, you know, that's actually a rhetorical question because I know the answer. And the answer is that we have all been trained not to see this. We've all been trained that the only way you can get more algal biomass in most freshwater systems is to add more phosphorus to the equation. And that's true for most algae, and it's true for most situations. But it's not true for Didymo. Why? What is it about Didymo that enables it to violate the holy grail of limnology? This is it. You're looking at it. And like I say, the question is whether you can actually see what you're looking at. And most people don't. This is a clump of Didymo on a stone from a river in New Zealand. Kathy, we never did figure out who actually took this picture. Oh, did you take it? Oh, I didn't know. I know. I thought you said that Kay Vole did. Oh, okay, excellent. That's even better. Okay, so you had the sense to cut this thing open and splay it open and show them what it is, and all of the living Didymo cells are on the very surface, and a very, very thin film of living Didymo cells here, sitting on top of a mass of extracellular, non-living carbohydrate. And then I tell my audience, based on the living to non-living carbon in these structures, Didymo isn't an alga. Didymo is a tree. How much phosphorus does it take to grow a tree? Anyway, so the conclusion of this is that the proximate cause of Didymo blooms is extremely low phosphorus. The culprit of blooms in the northern hemisphere, and I think elsewhere as well, is actually oligotrophication. Now, I don't know how much time I have. I have another few slides I can show, talking about what kind of a problem is Didymo? Why are we concerned about it? What's the issue? Well, first, it's an aesthetic nuisance. Everyone agrees with that, right? It looks terrible. There's no question about that. Second is it alters riverine food webs. And third is the potential for impaired fishery, although that's sometimes difficult to detect for a variety of reasons. Invertebrate communities, everyone who's looked at this has seen this same sort of shift from big-bodied insects on the left-hand side, Phemeropterans, Trichopterans, caddisflies, moving into the world of midges and chironomids that love thick organic mats. And this kind of a shift should be reflected in some kind of an effect on fish. But it's not always seen, actually, for a variety of reasons. And Kathy and Caroline will talk about some of that. This is a summary of the effects of Didymo blooms on fish. This is just from years of being in a position to sort of see what's been going on. And the bottom line here is that the effect of Didymo blooms on fish seems to be species specific. It depends on the fish. It depends on the severity of the blooms. And it depends on the feeding strategy of the fish. But I think it's important to ask experts from other countries about what their experience has actually been. And when I organized the first international workshop on Didymo in Montreal in 2007, I invited experts from around the world who had experience with Didymo blooms on fish communities in their rivers. And one of the people that I invited, Ileana Lindstrom, a friend of mine from Norway, a lot of historic knowledge about Didymo and about fish. And she came and presented to this Montreal meeting these results. That in rivers in Norway, some of the most productive Atlantic salmon rivers in Norway are rivers that have semi-continuous blooms of Didymo. And the same is true for brown trout production too. So in other words, if Didymo is affecting the production of these, it's difficult to discern with this kind of big scale sort of look or whatever. The other place that you can get advice from is Iceland. Iceland, blooms of Didymo started in Iceland in 1994, and the photograph here is testament to the blooms were horrific in a lot of rivers in Iceland. And after being introduced, or whatever happened, the bloom started in 94, it spread rapidly, and then it began to decline. And the bottom line here for the people from Iceland, and I've confirmed this recently by phone, I call these people up, I know them, that Didymo was never considered a nuisance by fishermen or by the government, and they never did anything to stop it, and it's not considered a problem today. Now, briefly about the history of Didymo as a species in the northern hemisphere. There's been several coring studies done. This one, I think, is one of the best. It's from a lake in southeast Alaska, Naknek Lake. This lake was cored, and Didymo was found all the way to the very bottom of this lake, so 800 years. As long as this lake has existed, Didymo has been there. Now, this is a special image. No one's seen this before. This is a frustule of Didymo from a deposit in British Columbia that's been accurately dated to 11,000 to 12,000 years before present. This is, I believe, the oldest Didymo frustule ever photographed. Didymo has been with us since the last ice age. It's always been. And there's never, but the important point, the reason I'm showing this, not that, is to indicate to you that in spite of the fact that it's been around for a long time, it's also very rare. Like the person who did this analysis of these samples counted thousands of samples before they found one Didymo. It's rare, but it's there. This paper, I know that Caroline will talk about this, but I only show it here to show one thing, and that is this nagging question about, well, okay, Didymo's been around for ages, okay, so what, you know? But maybe there was some new variant that came along or whatever. And this paper here actually puts the stop to that thought, because this paper is not fossilized material. These people found Didymo in cores, in systems, in the immediate years before the blooms began. In other words, Didymo was always in this system. It did not start blooming until 2006. But in the years leading up to 2006, it was there. In other words, the probability that this is a new variant is not eliminated by this, but it's pretty remote. There, I won't say any more. So, Didymo blooms are not your fault. Once blooms have started in a particular geographic region, where there's a suitable physical and chemical template for them to grow, the distribution of blooms is determined by the concentration of dissolved phosphorus. This final outcome has not been perceptively altered by control mechanisms. And blooms in North America are, now we have evidence that it's actually the result of climatic warming, enrichment of landscapes with nitrogen, and a number of other processes I talked about. There.